Our group project was for ammonia production chemical process. The ammonia compound is a very common compound used in fertilizers or household cleaners, and it's used throughout the world. The production of ammonia can be done with various methods, but the main idea behind engineering is to reduce the amount of waste and to reduce the amount of resources needed for ammonia production, thereby reducing the cost and making it consumer friendly. Now, our project gave us a description of a typical plant cycle where fresh feed is combined with a recycled stream into a reactor where it reacts stoichiometry. Then the gas stream is fed into a cooler, then condenses the ammonia out, and the remaining gases are fed back towards the stream, where one stream becomes a recycle, while one stream is purged out of the system. Now, in this problem for us, we were given three variables. We were given the mole fraction of the inert gas in the fresh feed, which is xi naught, and we were given the fractional conversion of the reactor, FSP, and the fraction of the gas leaving the condenser, YP, mole purged over mole total. Now, we had 4 different tasks to complete. First task is to find algebraic equations in order to find 3 variables. First variable was the total moles fed to the reactor, which is NR. And then the next is, if I scroll down, the moles of ammonia produced, and then the fraction of overall nitrogen conversion given below right here. So in order to find those equations, we have to do some algebra, which I will get into later. The second task was to graph these variables, alternating one or two variable in order to find the best possible yield for ammonia. And third task was based upon those graphs. We were to find the best possible method to come out with most amount of ammonia. And finally, the fourth task is to find the utility cost depending on whatever the user has entered. So first, I would say I can explain the algebraic equations, which we derived from one of the other reference videos. Let me show you that. These equations were given to us, where NR is the total number of moles fed into the reactor, and P is the number of moles of ammonia produced. So based off of these equations, we can do a mass balance equation for it to be right here at this intersection, where the recycled stream and the fresh feed meet and they combine into this value. So in order to find what each variable means, we would have to write them out in a mass balance equation, which I did over here, where I said N equals out. There were about 3 N1s for hydrogen. As you can see over here, 3 N1s plus 1 N1 equals 4 N1s plus N2. So 4 N1 plus N2. 1 is the total number of moles coming in, which is right here. And then this is a recycled stream, which is based off of here. So you can say add these two together, you get 4N1, and then this is N2. Now, N2, since N2 is the number of moles of the inert gas. Now, the inert gas is not going to react into any of this. So the number of moles coming in for inert gas is going to equal the number of moles going out. So N2 can be found using this equation right here, xi naught over yp. If we sub that back into this equation, use algebra to figure out what N1 is, which brings us down to over here. At this point, we can find N1 according to our given variables. Our given variables are xi naught, FSP, YP. And from there on, we find the moles of hydrogen by 3 times N1. And then over here, since our NP was 2 FSP N1, we can also find NP by using that same formula. And R is just the total number of moles fed into the reactor, which is 4N1 plus N2. And the overall fraction conversion of ammonia can be given by 4NP over 1 minus xi naught. Sorry, 1 second. And these are the given values, and these are the values that we are supposed to find. So in our code for MATLAB, what we do is we use those equations right here that we just saw, and I will go through the code and finish off all the tasks. Now in this code, what our main goal was to do everything into a function. And so the user is going to enter 3 variables, xi, FSP, and yp, and we will provide them with total number of moles of ammonia, number of moles fed into the reactor, and then FOV. For this video, I have slightly altered our code, so I won't be entering the values, but they will be randomly generated just to save time a little bit on typing. But the main thing is that these 3 values are in the real code provided by the user, as you can see over here. All I've done is commented out those lines, and I'm creating a random vector for all 3 of them. With this vector it's only one row with also a random number of columns. So each time we run the code, the 3 variables will have different values. So from our code, the first thing it does is once it creates a value, once the user enters the value, we send those values into our function called ammonia. In the function, first thing the function does is checks the size of the values entered by the user. Now in our case, right now, the number of columns will be the same because it's a random, but a user can enter different sizes. They can make a mistake. They can enter 2 columns for one, or 3 columns for one, or they can vary in the size. So first thing we do is in our code is we check and see if the user has entered the same number of columns or the same number of elements for each vector, xi naught, yp, and fsp. If it's not, then this error message will prompt the user that they have not entered the correct number, and then it will prompt the user to enter those values again. Now, in our case for now, we will not have that problem because all of our values are the same. But just as a runaround, let's say if I change this to 3, it should prompt us a warning saying the dimensions of the vectors don't agree and it won't work. So I will change that back to R. Now, when we go down after that, once we do the check and once we found out that everything matches up with all the elements are the same and the number of columns are the same, next we perform the operations according to our equations that we have found. Here, the variable N2